This is part B for Unit 5. And we've been going through looking at the different types of questions we can address when we do multiple regression. And I talked about 3 specific types of questions we can address when doing multiple regression. It would be good if you could actually review those and recall what those 3 questions are. Do you recall the 3 questions? So the first question is, what is the effect, which I have this represented by this frog up here, what is the effect of each x variable in predicting y, ignoring other x variables, ignoring the other predictors? So just ignoring x2, how much does x1 predict y? And that's indicated by this area in our Venn diagram. Area BC is the extent of overlap between x1 and y, simply ignoring x2. And then the second question, represented by this big happy orange frog, was to what extent do all my x variables taken together explain variance in y? So if I have two predictors, x1 and x2, to what extent do x1 and x2, when taken together, how much variance do they explain in y? And in our Venn diagram, that's indicated by area B and C and D. That's the extent to which both x1 and x2 overlap with y. That is the extent to which our 2 predictor variables taken together explain variance in y. And then our third question, represented by this meditating frog down here, was to what extent does each predictor explain variance in y, controlling for the other predictors in the equation? So to what extent does x1 explain variance in y, controlling for x2? And so for example, that would be represented by area B in our Venn diagram up here. Now, for each question, we want to consider 2 things. First of all, what is the effect size that will answer that question? And second, what is the inferential statistic that we can use to test the significance of that effect size? And so we want to be able to address those 2 things for each of these 3 questions. And you should be able to do that for the first 2 questions already, because that's what we talked about just a moment ago. So for our green tree frog up here, the question of what is the effect of x1 on y, just ignoring our other variables, what do we use to test the effect size? What effect size tells us about the relationship between x1 and y, ignoring x2? And that effect size is the regular bivariate correlation, which we indicate with a lowercase r. There should be an r there, lowercase r, just our regular bivariate correlation. The correlation between 2 variables is the effect size we use. Oh, there we go. Make a little better r there. Scribble that one out. So there's a nice neat r, our correlation. If we wanted to, we could square that correlation, but usually we don't. Usually we just leave it unsquared and report the bivariate correlation between 2 variables as simply a lowercase r. And then how do we test the significance of that correlation? Well, we test the significance of our correlation with a t-test. So the t-test, see if I can make a t there. There's a t. A t-test is what we use to test the significance of our correlation. And then for our second question, we also already talked about that, so you should be able to answer these questions. What is the effect size we use if I want to know what is the effect of all my predictors taken together in explaining variance in y? What is the total variance in y explained by all my predictors taken together? What is the effect size that answers that question? Well, that is the capital R squared. Now, we could use just capital R or capital R squared, but in this case, it's more common to square your multiple correlation. And recall that capital R is the same thing as a multiple correlation. So capital R and multiple correlation are the same thing. Capital R squared, multiple correlation squared, same thing. So, and the most common way is to use the squared version of our multiple correlation. Capital R squared is the effect size we use to determine what is the total percent of variance in y that's explained by all your predictors taken together. And then how do you test the significance of your squared multiple correlation? Well, we test the significance of that with an F test. We do an analysis of variance and calculate F. So now we're ready to move on to this third question. We haven't talked about this yet, so we're now ready to talk about the question of how do we determine, if I want to know what is the effect of x in predicting y after controlling for the other variables in the equation, how do I determine that? What is the effect size that will answer that question? And what is the significance test that I will use? What is the inferential statistic I will use to test the significance of that effect? And that is our next topic. And we will spend some more time talking about this than we did on the first two questions, because this is a rather interesting and complex thing to consider. So let's spend some time talking about how do we address that question. What is the effect of x in predicting y after controlling for other variables in the equation? So again, we've been looking at these three different questions, and the current question at hand that we're going to focus on is, what is the effect of each x variable controlling for the others? And let's start with asking, what is the effect size that will answer that question? And as it turns out, we can estimate that effect in several different ways, and we're going to talk about all of them. So we can calculate a beta weight. So in our regression equations, we will calculate betas, and when we're doing multiple regression, our beta weights will now answer this question of what is the effect of each x controlling for the others. And then we will also look at how we can calculate standardized betas. And we did this before when we looked at simple regression. We calculated betas and standardized betas. And we're going to do the same thing here. And we're going to see how when we do this in multiple regression, we're going to get the answer to this specific question. It's going to tell us what is the effect of each x controlling for the others. And then I want to talk about a couple other things that we can do that are related to betas and standardized betas, but we haven't talked about yet. We're going to talk about something called a partial correlation. And then I'm going to talk about something that's called a semi-partial correlation. And the thing that's called a semi-partial correlation can also be called an R-squared change, which is two names for the same thing. R-squared change, semi-partial correlation, two names for the same thing. And these are all different ways that we can answer this question, what is the effect of each x controlling for the others? So let's look at these different approaches and see what they are. So let's start by looking at the beta weights. Now, when you do multiple regression, when you have a regression equation with more than one predictor, then your beta weight will give you the effect of each x variable in predicting y controlling for the other predictors. The beta weights will answer that question. Now I want to look a little closer at exactly what the beta weights are doing. And there are two different ways that I want you to understand how a beta weight works. And if you understand both these definitions, or both of these ways of describing what a beta weight is, then you will have a good understanding of how beta weights function and what they are. So the first thing, and this first way is a little simpler, the second one will be a little more complex, but I think both are important. So first, we can say that the beta weight is the predicted increase in y for a 1 unit increase in x when all the other variables are held constant. Note that that definition is very similar to the definition I gave you before in our previous unit when we talked about simple regression. If I'm doing simple regression with just one predictor, then I said the beta weight is the predicted increase in y for a 1 unit increase in x, and then I just stopped there, put a period, and I didn't talk about any of this other stuff. But now, when we move from simple regression, where we have just one predictor, to multiple regression, where I have more than one predictor, now I say the beta weight is the predicted increase in y for a 1 unit increase in x when all the other variables are held constant. That's what happens when I add predictors to my equation. Now I get a beta weight that's giving me that effect for each x variable when all the other variables are held constant. Let's see what exactly that means. When I say all the other variables are held constant, one way of thinking about that is to say if all the other variables were the exact same value. So if I was doing a study where I wanted to predict, say, y was the extent of client well-being at the end of therapy, maybe I had people who were feeling depressed and they were receiving therapy for depression, and I wanted to predict how their well-being, how happy they were at the end of treatment. And maybe X1 was the extent to which they had a positive alliance with the therapist. X2 was the extent to which the therapist expressed positive regard towards the client. And X3 was the client's level of agreeableness. So what I'm going to say is that what would happen if, hypothetically, if I did a study where everyone in my sample received the exact same positive regard from the therapist, and everyone in my sample had the exact same level of agreeableness, what would be the effect of X1 on Y? What would be the effect of the alliance on the client's well-being if I had a sample where X2 and X3 were held constant? That is, if everyone in my sample had the exact same score on X2 and everyone had the exact same score on X3. And so what that would mean is that if X1, say the extent to which you had an alliance with a therapist, say that overlapped quite a bit with a therapist expressing positive regard. So, and maybe it overlapped to the point where they were almost the same variable. And so if your alliance overlapped with positive regard, and if I had a sample where everyone had the same positive regard, they experienced the same positive regard from the therapist, that would mean they would all have the same level of alliance. And so I wouldn't have any variance on alliance. Everyone would have the same alliance. And if everyone has the same alliance, it's not going to predict anything. It won't correlate with or predict Y if I don't have any variance on it. So if everyone has the same positive regard, and positive regard overlaps with alliance, then alliance can't predict my outcome. On the other hand, if positive regard and alliance are two different things and there's not overlap, and I hold everyone constant, if I say everyone has the same level of positive regard, but that still means I have lots of differences between people in the level of alliance, then that means it's still possible for alliance to predict my outcome, client well-being. So the question is, if I hold X2 constant, how much does X1 still predict Y? Or if I have two predictors, I'm going to hold both alliance and, or I guess this is the positive regard, and the client agreeableness. If I hold both those constant, how much does X1 still predict Y? And we'll do that the same for each of my predictors. So if I have X1, I could say, what is the effect of X1 on Y? Holding X2 and X3 constant. And then I can ask the question, what is the effect of X2 on Y? Holding X1 and X3 constant. And then what is the effect of X3 on Y? Holding X1 and X2 constant. So we'll look at it all three ways. Now, when I say holding a variable constant, I mean, what if everyone had the same score? So if I say X2, if that's the positive regard, if everyone had the exact same score for positive regard, and if X3, if that's the level of agreeableness, what if everyone had the exact same score for agreeableness? And mathematically, we could hold them constant at any value. So we could say, what if everyone had a score of 5 for positive regard? Or what if everyone had a score of 10? So we could pick any value and hold it constant at that value. And if we did that, we would actually get the same result. If we want to ask that question, what would the effect of X1 be on Y? Holding X2 and X3 constant, we could hold them constant at any value, a 3, a 5, a 10, pick any value. If everyone had the same score, regardless of what that score is, we would get the same exact result for how much X1 predicts Y. So it doesn't matter what value we hold them constant at. But to illustrate what's going on here and to clarify what's going on, it's easiest to think about it holding it constant at 0, even though we'd get the results the same if we did any other value. To understand what a beta weight's doing and to make our results clear, let's say this. We're going to hold everything constant at 0. So we're going to say if everyone had a score of 0 for X2, and if everyone had a score of 0 for X3, what would the effect of X1 be in predicting Y? And note that if everyone had a score of 0 for X2, then this part of my equation would become slope 2 times 0, because everyone has a score of 0 for X2. And if everyone has a score of 0 for X3, this part of my equation becomes slope 3, beta 3 times 0, because everyone has, hypothetically, a score of 0 for x3. And so what that means, if x2 is 0 and x3 is 0, this is how my equation comes out. I say the outcome variable y is equal to intercept plus slope times x1. That would be your slope, and this would be, say, the extent to which there's an alliance, plus slope 2 times 0, so that's just going to drop out, plus slope 3 times 0, that's just going to drop out, plus error, and so my equation would simplify to this. And note what I'm left with. This is just a simple regression equation with just one predictor, where I'm using alliance to predict the outcome variable, client well-being, and I don't have any other predictors. So if I held constant x2 and x3, and if I held them constant at 0, then these betas would drop out, and my regression equation would simplify to a simple regression where I'm just using x1 to predict y by itself. And so with that, we can think of this is telling us what the beta weight means. We can understand that in this multiple regression equation, this beta right here, beta 1, is essentially the beta weight we would get if x2 and x3 were 0 for everybody in our sample. That is, if x2 and x3 were held constant at 0 for everyone in our sample, this is the beta weight we would get. So that means, going back to our top here, that's why we can say the beta gives us the predicted increase in y for a 1 unit increase in x when all the other variables are held constant. And if we want to be more precise and clarify exactly what's going on here, we could say when all other variables are held constant at 0, it is the beta we would get. So this beta right here is the beta weight we would get if x2 and x3 were held constant at 0. And likewise, beta 2, this beta right here, gives us the effect of x2 on y if x1 and x3 were held constant at 0. In other words, if everyone in my sample had the exact same scores on those variables. So that's one way of understanding what a beta weight is. Now, the second way that I want you to understand what a beta weight is involves the idea of extraction. That is, how we can extract residual scores out of a variable. And we talked about that in our previous unit in simple regression. We talked about extraction, and I've got my extraction bunny over here, which is the same picture I showed you before when we were talking about extraction. And so building on this concept, we can say a beta, what is a beta? A beta is going to tell us if we have one or more control variables are extracted out of x and y, the beta is a predicted increase in the residual of y given a 1 unit increase in the residual of x. So again, a beta, if we're going to use extraction to define what a beta is, we can say if one or more control variables are extracted out of x and y, and then we'll get a residual of x and a residual of y with a control variable extracted out, then our beta is a predicted increase in the residual of y for a 1 unit increase in the residual of x. Let's take a closer look at how that will work. So here I have a regression equation with just two predictors. I say an outcome variable y is equal to an intercept plus slope 1 times x1, so x1 is my first predictor, plus slope 2 times x2, so I have my second predictor variable, plus error. And we could talk about how do we calculate this first slope, beta 1, which is going to be the slope of x1 predicting y, controlling for x2. Or we could talk about how we calculate the second slope, beta 2, which is the effect of x2 on y, controlling for x1. Let's focus on, just to keep things simple, let's focus on how we calculate beta 1, this first beta for x1. So using the idea of extraction, this slope for beta 1, we're going to say this slope for beta 1 is going to tell us about the extent to which the residual for x1 predicts the residual for y when our control variable x2 is extracted out of both x1 and y. So to do this, what we need to do is we need to take x2, we need to use x2, and we need to extract x2 out of x1, and we need to extract x2 out of y. And I have my picture down here. Here's a picture of y, and it's kind of faint here to say that stuff has been extracted out of y. So here's my y variable, and she's not all together there because stuff has been extracted out. So this is y. This is my y variable with x2 extracted out of her. And this is my x variable with x2 extracted out of her as well. So I've taken my x variable and I extract x2 out of y. And so this is the leftovers. This is the stuff of y that couldn't be explained by x2. And I take x2 and I extract x2 out of x1. And this is the leftovers. This is the residuals of x1 after x2 has been extracted out. And then I'm going to use this residual of x1 to predict the residual of y in a regression equation, and that is actually going to give me what beta 1 is. Beta 1 is actually what I get if I extract out the residual of x1, and if I extract out the residual of y, use the residual of x1 to predict the residual of y, and that will give me beta 1. Now, let's go through this process step by step to clarify exactly what is going on here. So, if you recall from our previous unit, if I want to extract one variable out of another, the one that's doing the extracting I could call the perpetrator, the one that's getting stuff extracted out I could call the victim. And so, if I want to use a perpetrator to extract stuff out of the victim, I use a regression equation where I use the perpetrator to predict the victim, and I get a residual. And that residual is the score on the victim variable with the perpetrator stuff extracted out. So, let's see. If I want to extract x2 out of y, so I want to get back up to my previous slide here, and it got so much marks on there. So I want to get this. I want to get that y with x2 extracted out of it. So I want to extract x2 out of y. That's the first thing I want to do. So how am I going to do that? I need to use x2 to predict y in a regression equation. And if it's helpful, you might even want to go back to our previous unit on simple regression and review the information on extraction just to clarify what we're doing here. But if I want to extract x2 out of y, I need to do a regression equation where I use x2 to predict y. So that's what I have right here. I'm going to say y is equal to an intercept plus a slope times x2. And I'll call this beta 2 because I'm calling x2, labeling that 2, so I give my beta weight the same number to match there. So I call it beta 2 times x2 because my variable is called x2. So I get a slope where I'm using x2 to predict y. And I'm just using my control variable. You could say x2 is the control variable. It's the perpetrator. It's the stuff that's going to be doing the extracting. Y is the victim. It's the variable that's going to have stuff extracted out of it. So I use x2, my control variable, to predict y in this regression equation. And when I do that, I'll get an error, a residual. And the residual is, for each person in my sample, how far that person's predicted score deviated from their, or how far each person's observed score deviated from their predicted score. That's residual for every person in my sample. And that error is going to be the new person's score on y with x2 extracted out of it. And that's the stuff we talked about in our previous unit on simple regression. We talked about how when we calculate these errors, we can think about those errors as the mistakes that we make when we use x to predict y. It's how far the observed score deviates from predicted score for a person. Or we can think about that error as the residual. It's your new score on y with x extracted out of it. And that's what we're doing here. We're going to think about it as the residual, the new score on y with x extracted out of it. Now, I want to put some subscripts down below my error here, and these will be important to clarify exactly what's going on. So pay attention to these subscripts. So I have the subscript here, error, y, period, x2. and read the period as controlling for. So what that means is this is the error for a variable y controlling for x2. In other words, it's the residual for y with x2 extracted out of it. So E subscript y period x2 means the error for y controlling for x2, which is the same thing as saying the error for y with x2 extracted out of it. So now this error right here, if I back up to my previous slide, this error is giving me this. It's the y with x2 extracted out of it. So now, now I need this. I need to get my residual for x1 with x2 extracted out of it. So now I need to get that. And so I will do an equation for that. Here's now this top part is what we've seen before. I'm just adding this equation down at the bottom right here is what I've added. And this bottom equation, I'm going to use x2 again. That's my control variable. So what we just did, we used x2 to predict y, and we extracted x2 out of y. We got that residual for y controlling for x2. Now I'm going to use that same control variable, the same perpetrator, but this time the victim's different. This time the victim is x1. I'm going to use my control variable x2 to predict x1 in a regression equation. So now I have x1 is equal to an intercept plus a slope beta 2 times x2. And again, I call this x2 because this is x2 in my regression equation up here. So I'm just keeping that same x variable, and I'm just labeling it x2 every time. And because I label this variable x2, I label my beta weight x2. And then in this equation, I get my error, or my residual. And at this point, it's the error. I'm going to give the subscript E subscript x1 period x2, meaning it's the error for x1 controlling for x2. Or in other words, it's the error for x1 with x2 extracted out of it. So now I've created two residual scores. I have the residual for y with x2 extracted out, and the residual for x1 with x2 extracted out. Again, let me back up to my picture here and just clarify. In our picture here now, we have the residual for y with x2 extracted out, and I have a residual for x1 with x2 extracted out. Now I have two residual scores. And at this point in my study, if I have a sample of people, so I had a sample of 100 people, everyone has a score on x1, everyone has a score on x2, everyone has a score on y. So I started off, everyone has three scores. I have three variables, x1, x2, and y. And then I use x2 to predict y and calculate the residual for y controlling for x2. And then I use x2 to predict x1 and calculate the residual for x1 controlling for x2. So now everyone has 5 scores. Now everyone has a score on y, everyone has a score on x1, everyone has a score on x2, and everyone has a residual, your score on y, with x2 extracted out, and everyone has a second residual, the residual score for x1 with x2 extracted out. So now at this point, everyone in my sample has 5 different scores for 5 different variables. Y, x1, x2, residual for y with x2 extracted out, residual for x1 with x2 extracted out. So now what we're going to do is I'm going to take this residual for y with x2 extracted out, and I'm going to put it down here and make it an outcome variable in a regression equation. And I'm going to take this residual for x1 with x2 extracted out, and I'm going to put it here and make it the predictor variable. So at the very bottom here, I have a regression equation where I say the residual for y with x2 extracted out is equal to an intercept plus a slope times the residual for x1 with x2 extracted out plus error. Note that at this point, this is now just a simple regression equation with one predictor predicting my outcome. The one predictor in this case is the residual for x1 with x2 extracted out, and my outcome variable is a residual for y with x2 extracted out. But this is just a simple regression equation with one predictor. And at this point, we have just now calculated beta 1 for our multiple regression equation. This beta down here at the bottom in my last equation, where I used the residual of x1 to predict the residual of y in a simple regression equation and get the beta weight, and this beta 1 right down here tells me what is the expected increase in the residual of y, controlling for x2, given a 1 unit increase in the residual of x1, controlling for x2. That's what beta 1 tells me. And that beta 1 is exactly what the beta 1 is up here in my multiple regression equation with multiple predictors. That's what beta 1 is. If you recall, I mentioned before that the typical way of calculating intercepts and slopes when you do multiple regression is to use formulas that involve matrix algebra. And I skipped over those formulas because they could take a little while to explain the matrix algebra, and I wanted to get on to other things. But now I've actually given you a way that you can actually calculate what these beta weights are without using matrix algebra. So if you want to calculate what is beta 1 from this multiple regression equation, and you want to do that without using matrix algebra, you can do it this way. You extract x2 out of y, you extract x2 out of x1, and then you take the residual of x1, controlling for x2, to predict the residual of y, controlling for x2, and you get this beta weight right here. Now you've got a beta weight from just a simple regression equation. And in our unit on simple regression, I gave you the formulas you can use to calculate that slope. That's just the covariance between our two variables divided by the variance of x. And so you could calculate what that slope is, and that slope is exactly what you would get if you used the usual matrix algebra approaches to calculating your intercepts and slopes for multiple regression. So I've just told you how you can calculate beta 1 in multiple regression in a process where you extract x2 out of everything and then use the residual of x1 to predict the residual of y, and there you have it. This beta weight from our simple regression equation is the beta weight you would get if you did a multiple regression equation. And so that both gives you one method you could use to calculate betas if you wanted to, and more importantly, and the key reason why I'm going through all this, is that I want you to understand what the betas are. And so if you understand that this beta from the simple regression equation, where you use the residual of x to predict the residual of y, is the same thing as a beta you get when you do multiple regression, then you understand what the betas are for multiple regression. You understand, what does this beta 1 mean? What exactly does it mean if you do multiple regression and you have two predictors predicting an outcome variable y, and you get a slope for beta for x1? What does that slope mean? What does it tell you? So now you know click the button. Now you know one way of interpreting what that slope means is it's what you would get if you extract x2 out of everything and then use the residual of x1 to predict the residual of y. And that's what this beta 1, that's what it's telling you. That's what you get. That's what it means when you do a multiple regression equation and calculate a beta weight. And this slide is just showing you that same equation with the picture of that residualized caret placed in the proper location. So this is just again showing you this is the residual for x1. So there we've got our caret, and she's had stuff extracted out of her. In other words, x2 has extracted everything it can out of x1, and this is the residual. She's not all there. Some stuff has been extracted out. So that's the residual for x1 with x2 extracted out. And over here I have the picture. This is the residual of y with x2 extracted out of y. Again, she's not all there. That's that residualized caret with some stuff extracted out of her. And so again, our equation is saying, to what extent does the residual of x1 explain variance in the residual of y? That is, what is the expected increase in the residual for y given a 1 unit increase for the residual of x1 if x2 has been extracted out of both x1 and y. So those were all the steps we would take if we wanted to calculate beta 1 in a regression equation with two predictors, x1 and x2, both predicting y. Now we can go on and we can consider, how would we calculate the beta weight for x2? And we will do this in exactly the same way. The only difference is x1 and x2 are going to trade positions in terms of where before x1 was a predictor and x2 was the control variable or the perpetrator extracting variance out of every one. Now, if I want to get the beta weight for x2, x1 is going to become the control variable. It's going to be the perpetrator extracting variance out of every one, and x2 will be the thing that's trying to predict y. So we'll go through all the same steps again. So I want to get the residual of y now controlling for x1. So I use x1 to predict y in a regression equation and get this residual. The residual for y, period, x1. The residual for y controlling for x1. And then I want to extract x1 out of x2. So I get x1 predicting x2. And so x1's the perpetrator, x2 is the victim now. I use x1 to predict x2, and I get this residual. The residual for x2 controlling for x1. And then I take the residual for x2 controlling for x1, and I use that to predict the residual for y controlling for x1 in a regression equation. So residual y controlling for x1 is equal to intercept plus slope times residual for x2 controlling for x1 plus error. And this beta right here, this beta 2 in my final equation is identical to beta 2 from this top equation, which is multiple regression. So the bottom equation, this simple regression with just one predictor, using the residual of x2 to predict the residual of y. This beta weight I get here is the same thing as the beta weight I would get in a multiple regression equation in which I use both x2 and x1 to get y. So that shows us how we can understand beta 1 is the extent to which x1 predicts y controlling for x2, that is, with x2 extracted out of everything, and this beta 2 right here is the effect of x2 predicting y controlling for x1, that is, if x1 is extracted out of everything. So that gives you another way of understanding what beta weights are when you do multiple regression. And that is everything for part B of Unit 5.